So in our last class, we were looking at understanding the basics of electricity. That is understanding what is a charge, how charges work, and understanding the three pillars of current electricity, which is current, voltage, and resistance. So we were trying to also understand the basics of magnetism, understand what is a magnetic field, understand how it behaves, what are magnetic poles, how do they interact. And we were also trying to understand through charges the behavior of electric fields consequently. What I did not do, however, is try to link these concepts. So part one was more about understanding magnetism separately and electricity separately. So for part two of the revision, I'll combine these topics and then I'll revise all the different rules of electromagnetism that you have learned or are going to learn going forward. So let me begin. So again, I'll brush a few concepts here and there, specifically the key aspects that I'll take for the next part. Now, make note of a few concepts that I'm about to revise. So notice here that a magnetic field consists of two poles, that is a north and a south pole. The direction of the magnetic field lines are always north pole to south pole outside of the magnet and south pole to north pole inside of a magnet. In other words, they always form a closed loop. Very, very important. Please notice they always form a closed loop. Again, this is the pattern as seen by bar magnets sprinkled with iron filings. Again, we've discussed this as well. The earth also behaves like a magnet. One small mistake in this picture. This is supposed to say magnetic south because this is the south pole. This is supposed to say magnetic north because the north pole is here. So the magnetic north pole is near the geographic south pole. The magnetic south pole is near the geographic north pole. Very close, but not exactly the same. This small angle, I did tell you guys to research what it's called. It's called the angle of depth for those of you who are interested. Now, let's understand the magnetic effect of current. Before we understand magnetic effect of current, a brief revision again of three concepts: current, voltage, resistance. Current is denoted by the symbol current is denoted by the symbol I. Its unit is ampere, denoted by the symbol A. Current is a formula, I is equal to Q by T. This is because current is defined as the rate of flow of charges at a given point. Current is a scalar, no direction. Q can also become N into E, where N is the number of charges, E is the value of each charge or value of charge on each electron or a proton, which is a constant, by T. In terms of Ohm's law, current I is also V over R. Next. The next concept we learn is voltage, which is given or which is dictated also by three other names. That is potential difference, potential, and EMF or electromotive force. The symbol regardless for all of them is V. The unit is volt, whose symbol is also V. Let that not confuse you. V is equal to work done per unit charge. V is equal to current into resistance. V is equal to the potential difference between the final and the initial points as well in a circuit. The last concept you've learned is resistance. Resistance is denoted by R. Its unit is ohm, the Greek letter for omega. R is equal to V by I in terms of Ohm's law. R is also equal to, again, remember, when you're using V by I, you are assuming that the length and the cross-sectional area are remaining a constant, which is why resistance is a constant. In the formula, R equals V by I. But if you're changing either the length or the cross-sectional area or both, then the formula becomes rho into L divided by A. Here, rho is not density, like in mechanics. Rho is the resistivity of a material, which is the resistance per unit length per unit cross-sectional area. Resistance will change with length and area, but resistivity will remain a constant and will change only if the material of the wire is changed. Please remember that. Also, for series and parallel circuits, we have discussed this. For a series circuit, current is going to remain the same. Voltage is going to differ. In fact, it's going to be added for a cascading series circuit. And for a parallel circuit, voltage is going to remain the same for two components which are in parallel to each other. But the current is going to split, and the individual currents can be added to get the total value of current in a parallel circuit. Next. So let's understand the concept of magnetism and electromagnetism using a few rules. There are, strictly speaking, three rules according to your textbook. One is called the right hand thumb rule, which is again dictated by many, many names. It's called the right hand thumb rule. It's called it was called Ampere's swimming rule in a way, in a different context a while ago. It's also called the right hand screw rule, but the meaning is the same, regardless of what you call it. And then there are two more rules. One is Fleming's left hand rule, which is used for an electric motor. The other is Fleming's right hand rule, which is used for an electric generator. There are, however, rules which are additionally written for charges behaving in a magnetic field, which are again an extension of Fleming's rules. I will teach it to you guys as a separate rule. You can understand it to be an extension of Fleming's rules itself. It does not matter. Let's start with the right hand thumb rule, the right hand grip rule. I'll give you the context to the rule and then explain the rule. The right hand grip rule is used in a very, very, very simple context. It is used to find the direction of magnetic field produced by a current carrying wire. That's it. A current carrying wire. Please note, there is no force in this rule. Why is there no force? I'll explain in a while. First, let me explain the rule. So what does the rule say? The rule says if you hold the right hand as given in the diagram, if you hold your right hand like this, like a thumbs up, like this, then if your thumb indicates the direction of current or the conventional flow of current, positive to negative, through a wire, then the direction in which the other four fingers curl around your thumb gives the indication or the direction of the magnetic field that is produced by the given current carrying wire. In other words, current flowing through a wire is straight, then the magnetic field produced by it is around the wire and it is circular. Please remember this. That's all the rule says. I'll explain the rule again in a different way. So if this arrow mark indicates the direction of current flowing through a wire, and if I hold my thumb in this upward direction, then you will notice that as I look at it, my fingers appear to curl around this wire in an anti-clockwise direction. So that is exactly how the magnetic field pattern is around this wire. So if I were to show you the same. So if this is a plane that I've considered, please remember I am looking at my wire like this. So if this is my wire, I'm looking at it like this. So as seen, the current appears to be in the anti-clockwise direction. Please notice I am drawing the magnetic field lines closer to each other on purpose, closer to the wire. But as I go farther away, I will draw the magnetic field lines farther and farther apart. The magnetic field lines will be closer to the wire because the magnetic field strength is greater, much closer to the wire. And logically, as you go away from the wire, the magnetic field lines get weaker and weaker. Please make sure to clear all your doubts. If this is my current carrying wire and this tip indicates the current direction, which is upwards like this, then the magnetic field pattern around the wire is like this. It's like this. and it is not present at one particular point or one particular area. It is present throughout the wire. So around the wire, there is a magnetic field pattern produced in a circular direction. There is no north or south here because it's a closed loop. Please remember this. It's a closed loop. The point of view I'm you viewing it at doesn't allow me to write a north or a south pole. You can assume a north or a south pole in any direction. It does not matter. Just remember the magnetic field lines go in a closed loop around this wire or around this current carrying wire. Next, the next part is the right hand thumb rule or the grip rule being applied to a solenoid. So what is a solenoid? A solenoid is just a current carrying wire which is in the shape of a coil. That's the only difference. So if instead of this current being straight, if it's in the shape of a coil like this, this is a solenoid. That's it. So let's take a direction of current in a particular direction. Let me redraw this. I think I deleted it by mistake. Okay. So let's connect this to a supply so that I'm able to produce and allow current to pass through it. Current conventional flow is obviously positive to negative. I've explained this. Let's say current goes like this. Current goes. This is the front part of the wire. I'll highlight the front part in red. The front part of the wire is this. The back part of the wire, I'll highlight in green like this. So the front part is red. The back part is green. So in other words, to me, how I'm looking at it, this is the direction of current. Please notice, this is the direction of current. Let me unblur my background. I think you guys will be able to see this better. Yeah. So to me, the front part of the wire, the red part, is where the current is going down. So the front part, current is going down like this. So my thumb will now indicate the direction of the magnetic field through the coil, or some people also understand it as the direction of the north pole of the magnetic field produced. Think of it that way, it doesn't matter. These four fingers now will instead indicate the direction of current. So just to recap, for a straight wire, thumb is the direction of current. The other four fingers are the direction of the pattern of the magnetic field around it. For this, it's the opposite. Here now, the thumb will indicate the direction of the magnetic field or the north pole of the magnetic field produced. And these four fingers will indicate the direction of the current flow. I have assumed the red part to be the front part. I know it's difficult for you to imagine it because of the way I've drawn the diagram. Hence the colors. Imagine the red part to be the front of the coil where current is going downwards. So see, my four fingers are going downwards in front of me. So as I look at them, the current carrying wire is having current going down like this, and behind it's going back up, denoted by green. And as I see it, please notice the thumb is towards my right. The thumb is towards my right, which means towards the right of this coil exists the north pole of the magnetic field, and towards the left naturally exists the south. And through the coil, the magnetic field pattern will be a straight line. I'll repeat again. Through the coil, the magnetic field pattern will be a straight line as seen here. Through the coil, the magnetic field pattern will be a straight line. And obviously outside, it will go north pole to south pole, forming the closed loop pattern that we have known to understand. Again, I'm drawing more closer field lines closer to the poles and closer to the coil. As you go farther away, I'll draw less and less number of field lines. Please notice this magnetic field pattern is exactly the same pattern you see for a bar magnet. In fact, I'll keep the picture on board and I'll go back and show you. Notice it's the exact same pattern that you have for a bar magnet. Please notice. The diagram is just inversed laterally. That's it. So understand the right-hand thumb rule. This is the essence. Current is straight, magnetic field around it is circular. Current is circular through a coil or through a solenoid or through a loop. Then magnetic field through it will be straight. Very important grammar. Magnetic field lines through it will be straight. And around the coil, magnetic field lines still do form a closed loop, exactly like they do for a bar magnet. So right-hand thumb rule, not just applied for a straight wire or for a solenoid. It's in fact applied for both a straight wire and a solenoid. It's called a solenoid if it doesn't have like a metal bar in the middle. If you place a metal bar, then the metal bar can behave as an electromagnet. Hence the name, specifically electromagnet. That's it. So this is the right-hand thumb rule. Next, again, here you can see if it's a coil, the magnetic field lines through the coil will be straight. Here they've shown a single coil. I showed multiple coils to make you understand better. Again, here it is. Magnetic field lines through the coil will be straight if coil is circular. If current is straight, then magnetic field around it will be circular. That's it. Straight circular. Think of it that way. Now, look at a few features of the magnetic field produced by the current carrying coil. The field is similar to that of a bar magnet, and there are magnetic fields at the end. Increasing the current will increase the strength of the field. Increasing the number of turns of the coil, not number of coils, number of turns or rotation of the coil will also increase the strength of the field. So the strength of the field can be increased by either increasing the current or the number of turns. Reversing the direction of current will reverse the poles of the magnetic field produced. That's it. I'll repeat again. Reversing the direction of current will just reverse the reversing the direction of current, will just reverse the poles of the magnetic field that is produced. The north and south pole will just interchange positions. That's it. Again, here you can see the right hand thumb rule being used for a coil instead of a wire. For a coil, these four fingers now indicate the current direction, thumb will indicate magnetic field. For a straight wire, thumb is current, the four fingers indicate the pattern of magnetic field around it. That is right hand thumb rule for you. Now this begs the next question. What about force? Why is there no force in this right hand thumb rule that I explained so much? There's a very simple reason why there is no force. Think of it this way. Force exists when there are two magnetic fields interacting with each other. I'm sure you guys have all played with magnets before, or you've at least seen magnets. You know how they behave in general. So notice, if I have just a single magnet in my hand, this magnet won't experience any force. But if I have two magnets in close vicinity with each other, then those two magnets will interact with each other because they produce two separate magnetic fields. And when two magnetic fields interact with each other, that is when a force is produced. So general rule of thumb, one magnetic field cannot produce a force. Two magnetic fields interacting with each other will produce a force. Please remember that. This is an electromagnet. An electromagnet is just a coil of wire with a metal bar placed in the middle. What happens is, as current passes through the wire will start to produce its own magnetic field. This magnetic field will magnetize the metal bar in the middle. The magnetized metal bar will then behave as an electromagnet. That's it. So how do you increase the strength of an electromagnet? Increase the current, increase the number of turns. Reversing the current will reverse the poles of the electromagnet. That's it. How do you demagnetize? One simple way to demagnetize, you can see here. So the magnet is slowly pulled out of a solenoid through which alternating current is passing. So alternating current is, you know what alternating current is. There are two types of current, alternating and direct current. Alternating current is that which reverses the direction every half a cycle, whereas direct current flows in the same direction throughout its entire existence. So as alternating current is flowing forwards, backwards, the magnetic field produced also changes direction rapidly. This rapidly changing magnetic field will help demagnetize the given magnet. Next, you need to also understand the advantages that electromagnets have over regular magnets. One of the simplest advantages is that you can turn on and turn off an electromagnet, which you cannot do with a permanent magnet made out of a ferromagnetic or even a paramagnetic material. You can reverse the direction of the poles, or you can reverse the north and the south pole in an electromagnet by reversing current, which you cannot do in a permanent magnet unless you demagnetize it and then magnetize in the opposite direction. And another important difference is you can increase or decrease the strength of an electromagnet very easily just by increasing or decreasing the current and the number of turns. But it is slightly, or it is increasingly more difficult to alter or manipulate the strength of a permanent magnet, because you will have to follow the methods of magnetization and demagnetization. The next device that you have, whose concept we need to understand, is a magnetic relay. The purpose of a magnetic relay is to use a switch connected to a low power supply to turn on the switch, or to turn on an appliance that is connected to a high power supply. How does this work? It works on the magnetic effect of current. How does it work? Very simple. As soon as you close the switch, current will start to flow through the wire. And in fact, current will also start flowing through this coil, the one that you notice here. This one. As current flows through the coil will get magnetized. And when the coil is magnetized, this iron armature will then bend down, because the iron armature is made up of soft iron, which can get easily magnetized, easily magnetized and demagnetized. By the way, if you're wondering, the coils are made up of not soft iron, they're made up of copper, because copper is a very good conductor. Anyway, now the iron armature will bend because it is attracted to the electromagnet. When it bends, it will, I think it will establish the contact here. And when it establishes contact, the switch is closed on this second circuit on the right hand, which will then allow current to flow in this part of the circuit. Whenever you open the switch again, the current will stop flowing, which means the magnet will get demagnetized, or the coil will get demagnetized, which means the iron armature will stop getting attracted, go back into position, because it would have been connected to a spring, which will spring it up back into position. And when that happens, the power supply is cut for the second circuit on the right as well. This is how you can use a relay, or this is the principle of working of a relay. Next, here you have a normally open relay, normally closed relay, the two types of relay. Next, a circuit breaker. What is a circuit breaker? Please remember, a circuit breaker is basically a fuse that can be used again and again and again. That's all. It works on the exact same principle that we have understood for magnetic effect of current. That's all. Now comes the important concept, that is magnetic force of current. So a current carrying wire, which is placed in an external magnetic field, can and will experience a force. Again, why does force come into picture here if it didn't come in the previous picture? The previous picture, there was only one source of magnetic field, which was a current carrying wire. Here, there is a current carrying wire and there is an external magnetic field. So when the current carrying wire, which is producing its own field, interferes or interacts with an external magnetic field, when these two magnetic fields interact perpendicularly specifically, that is when there is a force that is produced, or there is a force that exists. This force will be acting on the current carrying wire. Please remember this. So this brings us to the next concepts, two important concepts, in fact. One is the working, or the Fleming's left-hand rule and its application, which is the electric motor, and then Fleming's right-hand rule and its application, which is the generator. So I'll give you guys a quick 5-minute break. Please take this break. I will return in 5 minutes and we will complete motor, generator, and all the other topics that we need to be covering. transformer, so on and so forth. Hi guys, let's continue. So we've understood the magnetic force of a current. Remember, force will exist when there are two magnetic fields interacting with each other. That's just an easy way for, I'm just breaking down concept on a very, very macro level, not a micro level, but I'm just making it easy for you to comprehend. When there is force, when there is no force. A single current carrying wire, which is a single source of magnetic field, no force. A current carrying wire present in an external magnetic field, then there are two sources. One is the current carrying wire producing its own magnetic field. The other is the external magnetic field, usually from the north and south poles of a permanent magnet. When those two magnetic fields interact with each other perpendicularly, such that, think of it this way, such that the current direction and the magnetic field direction are perpendicular to each other, then there is a force that exists. And this force will be perpendicular to both the direction of current and the direction of magnetic field. So the only way that can exist is this way. So this is the current, this is the magnetic field. This will be the direction of force produced. This is called Fleming's left hand rule. So let's understand what the rule is, how do you use it. Okay. So here's a simple example. So in questions where you have to find out the direction of force, or let's say the direction of current, if it were Fleming's right hand rule, doesn't matter which rule, you always have to take a perspective. So I'll use one simple perspective that I ask all my students. Imagine you are looking at the computer screen. Okay. You have 6 possible directions. This is left or west. This is right or east, up or north, down or south. The 2 other directions are into the page or into the screen. And the other one is out of the page or out of the screen. I will explain all directions in terms of these 6 words that I've used. Okay. So let's take a point of view. I'll take a point of view of a person standing here. So for a person standing here, this is his or her eyesight. So you'll notice that for this person, the direction of current, the current is literally coming towards them. Correct? Can you see here? Direction is current is coming towards them because this is negative, this is positive. So this is the direction of current, as you can see. So current is coming towards them. We call that as out of the page. Next, what is the direction of the magnetic field? I've explained you this. The magnetic field, especially when you notice the north and south poles, the direction of the magnetic field is always north pole to south pole. Here, north pole to south pole is to the right from the point of view of this person. You can notice north pole to south pole is this direction, which is to the right. So current, middle finger, out of the page or towards me. This is towards me. Magnetic field to the right. So look at this. Please hold the fingers as such. This is Fleming's left hand rule. Hold the fingers such that they are always mutually perpendicular to each other. Whatever you do, when you rotate your wrist, don't bend your fingers. Hold them exactly the way that you are holding them right now. So when you hold them like this, current out of the page, magnetic current out of the page towards me, magnetic field to the right or to the east, the force acting is upwards or north. So this is how I figure out the direction of force, which is upwards or to the north. So this is how the force acts on this wire. This is how you use Fleming's left hand rule. As simple as that. Again, this is Fleming's left hand rule. Left hand rule is used specifically to find the direction of force acting on a current carrying wire placed in an external perpendicular magnetic field. In order, force, magnetic field, current. Force, magnetic field, current. The first 3 fingers, thumb, index, and middle finger. Next, we have to understand the turning effect of a coil. So you can use this force for acting on a coil to rotate a coil. This is called the turning effect, or also known as the motor effect. So what I'll do is I'll explain this through the working or the functioning of an electric motor. So it's going to be a while. So please make sure you don't lose your attention along the way. The setup is very simple. There is a rectangular coil that is placed between two powerful north and south poles of a permanent magnet. So this is my rectangular coil placed between two powerful north and south poles of a permanent magnet. This is a U-shaped magnet. So here you have a commutator which consists of a split ring, SPLIT. They're called split because they're exactly split in the middle, and a carbon brush. So let me name the split rings so it's easier for you. So I'll name this split ring S1, this ring as S2. I'll name this brush carbon brush B1, this brush B2. This is a simple DC battery, not just any battery, DC, which means the direction of current doesn't reverse. It remains the same throughout for eternity in its operation. Now, let me, in fact, name the rectangular coil. I'll name the rectangular coil as P, Q, R, and let's name this corner as S. Okay. So let's look at the direction of let's look at the setup as shown. As shown, this is how the coil looks. So this is, let me redraw. Actually, just shape correct. Let me just do this. This is easier. So as seen, I'm trying to draw the top view of this. The top view again, assume that this is the setup. This is the setup. This is the setup. Okay. So this is your coil P, Q, R, and S. Now, as the coils are in the alignment as shown, or the diagram shown here, or my drawing of a top view here, no matter which one you look at, you'll notice that current follows this direction. So current will go from brush B2 to S2. From S2, it will flow here. It will flow from S to R, R to Q, Q to P, P to in this direction, and then downwards, and then through S1 to through B1, through this direction, and then finally collect at the negative here. So current is going from S to R and from Q to P. So what happens here is, as current flows, please notice, current is flowing through four parts of the wire, through parts PQ, QR, RS, and SP. Whereas the axis of rotation is like this. I hope you notice the axis of rotation. This is the axle, which here acts as the axis of rotation. Okay. So that means the coil can just rotate like this or like this around this axis. Around this axis. Now, the four parts of the wire will experience forces. Let's first figure out the directions and then let's figure out the rotation. So for part PQ, I'll take part PQ of the wire. Current is denoted by I. Magnetic field, it's important to realize that magnetic field, sometimes your teacher might use M, but the actual notation that's supposed to be used is B. So, and F stands for force. For PQ, assuming front as my point of view or perspective, for part PQ of the wire, current is out of the page and magnetic field is north to south, that is to the right. So through Fleming's left-hand rule, current out of the page, magnetic field right. So force is upwards. So force acts upwards here. Here, upwards. Next, through part RS of the wire, current is into the page, as seen, exact opposite. Magnetic field is still right, which means force acting will be the exact opposite, that is downwards. You don't have to take my word, you can confirm. So current is out, current is into the page shown. Magnetic field is still to the right, force acting is downwards. Now, if you notice, these two forces, F1 and F2, which are acting on PQ and RS, form something known as a couple. A couple is just this. For a rectangular coil, two forces acting equidistant from an axis of rotation, basically rotating the body, are known as or are called as a couple. So they rotate the body like this. But as soon as the body completes half a rotation, I'll tell you what will happen. Half the rotation means P will come here, Q will come here, R will come here, S will come here. Because it's a DC battery, the direction of current doesn't reverse. So if the direction of current doesn't reverse inside the coil as well, PQ will be downwards, or PQ will be again like this, RS will be upwards like this, which means the force acting will now be reverse. So force left side it is up, right side is down, half rotation. Now right side is up, left side is down. So rotate like this. I don't think this is how you want a coil to rotate. You don't want a coil that rotates like this. You don't want it to complete half the rotation like this, and then the other half like this, and then like this. This is not how a motor should rotate. A motor should rotate in the same direction throughout, like this. So how do you make sure that occurs? Very simple. To make sure that occurs, what we do is use a commutator setup, which is a split ring in the carbon brush, to reverse the direction of current only inside the coil. How do we achieve that? Very simple. Notice during the first half of the rotation, split ring S1 will be connected to carbon brush B1 and split ring S2 will be connected to carbon brush B2. This is how the split rings are, S1, S2. As soon as they do half rotation, notice what happens. As soon as they do half rotation, S1 will now remove or get rid of its connection to brush B1. It will now be connected to brush B2. So S1 will come here, which will now be connected to brush B2. S2 will come here, which will now be connected to brush B1. So the direction of current here is the same, but the direction of current inside will be reversed. So what do I mean by reversed? That means PQ will now experience current direction upwards, RS will experience downwards, which means now for PQ, the force acting will be down, like this, down, which was originally the direction for RS. And RS will now have the current acting up, which was originally the direction for PQ. So thereby, by reversing the direction of current only inside the coil, you make sure to keep the coil rotating in the same direction. This is how, by reversing direction of current only inside the coil using the commutator, the split ring and the carbon brush setup, you make sure the rotation occurs in the same direction. So for the second half, again, please write your own directions again. If you want, let me keep this image here. For the second half, again, PQ, RS. PQ will now experience current into the page and magnetic field is still to the right, which means it will experience a force that is downwards, and RS will experience current out of the page, magnetic field still to the right, which means it will now experience a force that is upwards. So as they rotate, the direction of force acting on each coil will reverse, thereby making sure the coil rotation is in the same direction. So right now, as I see it, the coil rotation was happening clockwise. As soon as half the coil is completed, current reverses. The rotation will continue to happen clockwise. So that's how one complete rotation occurs. This keeps on happening infinitely as long as the motor is switched on. If you're wondering why PS and QR, I did not consider at all. That's because PS and QR, yes, they do have force produced, but it's just that they are not aligned along the axis of rotation. So the forces that are acting on both the wires, PS and QR, will be opposite directions, acting not along the axis of rotation. So thereby, they'll just keep the body fixed because they will cancel each other out. So the forces acting on PS and QR will cancel each other out. That is why I'm not considering them. This is the working of an electric motor, plain and simple. This is the action of the commutator. Again, explained in my own words. Here you can see the rotation. As they rotate like this, S1 will connect to B2, S2 will connect to B1. That's how current direction is reversed only inside the coil. If you're wondering why I cannot just use an AC battery, because AC automatically reverses the direction by itself, that's because AC is generated through a generator. You can't use a generator as an input for a motor because generator is produced by converting mechanical to electrical. If you give it as an input to a motor, it will just convert electrical back to mechanical. So what's the point of converting mechanical to electrical back to mechanical back to electrical? So it's like it's an unnecessary loop that you make. So this is the working of a magnet. Sorry, a motor. Remember, the turning effect of the motor can be increased by four things: increasing the strength of current, using stronger magnets, increasing the number of turns in the coil, or increasing the area of cross section of the coil. The rectangular area, you can increase that as well to produce a stronger turning effect. Next, before we understand the working of a generator, it is important to understand what is electromagnetic induction. So let me explain what electromagnetic induction is. Electromagnetic induction, as the name suggests, is the current or EMF being induced in a current carrying coil when it is subjected to a changing magnetic field. That's it. I'll rephrase it in my own words. I'll type it also. Electromagnetic induction is the phenomenon of current. You can call it current, you can also call it EMF. Both are same. I mean, I know they're not same. I know current is current, EMF is voltage. But in context to current flowing or being produced in a wire, you can interchange the words, it won't matter. Current or EMF produced or induced in a current carrying wire or a coil when the wire or the coil is subjected to a varying magnetic field. You can call a field as a flux as well. Your higher grades friends might tell you flux and field are different, and they are correct. Flux and field are two different quantities by definition and by usage for higher grade students. But for you guys, you can interchange the word field and flux as well. Just like how you can interchange current and EMF, it won't matter for you guys. Okay. The strength of induced EMF can be altered by three factors. One, moving the wire faster, or basically increasing the relative speed or the relative velocity between the coil and the source of the magnetic field, which it is being subjected to, using a stronger magnet. So it is subjected to stronger changes, and increasing the length of the wire in the magnetic field, or increasing the area of cross section of the loop, or by increasing the number of turns. That's it. So this explanation for electromagnetic induction is given through Faraday's law of electromagnetic induction, which basically states the EMF induced is proportional to rate at which magnetic field lines are cut. Or you want me to simplify this? What this says in complex words is just the EMF or the voltage induced is proportional to rate of change of rate of change of magnetic field or flux. Doesn't matter. Magnetic field or flux. Doesn't matter. Which one. So here is, in fact, these are oysters experiment. You can Google the again, YouTube it if you want. So what happens is, if I take a current carrying coil and if I take a bar magnet, let's say, as soon as I bring the magnet closer or even farther away from a coil, current will be induced in this coil. Remember, I don't just have to bring the magnet closer to the coil. When I bring it closer, current is induced. When I take it away, current is induced. It is just that when I bring it closer, current is induced, let's say, in one direction. When I take it away, current will be induced in the opposite direction. That's it. That's the law of electromagnetic induction. Now, please remember, there is another law or a rule you have to understand. It's known as Lenz's law. Lenz's law is basically a fancy name for law of conservation of energy. I'll explain you how law of conservation of energy comes into picture here. Law of conservation of energy. Law of conservation of energy. Now, law of conservation of energy, what does it say? The actual term is energy can neither be created nor destroyed, but can be transformed from one form to another. What it says is, in general, you cannot get energy for free. In order to produce or in order to get energy in one form, you have to always convert it from another form. Or in other words, you have to do work to get work done. That's it. As simple as that. Nothing is for free, especially in physics. Nothing is for free. In order to get work done, you need to do work. So basically, producing EMF in a coil is basically doing work, correct? But how do you do work? You is getting work done. I'm sorry. And how do you do the work? By pushing and pulling the magnet. And when you push or pull a magnet either towards a coil or away from a coil, you should ideally and even practically experience a resistive force. You should experience some sort of resistance. I'm not talking about resistance from gravity. I'm talking about this horizontal. When I try to push it, I should experience some resistance. When I try to pull it also, I should experience some resistance. This resistance is what Lenz's law is all about. Lenz's law basically says that whenever you try to push or pull a magnet, or whenever you try to subject a coil to a changing magnetic field by bringing another bar magnet closer and farther, the coil will produce current. Correct, true. Faraday said that already. But the coil will produce current in such a direction that the current produced by the coil will produce, use Lenz's law again, sorry, use right hand thumb rule. The current produced will produce its own magnetic field, north and south, which opposes the motion of the magnet, which is causing it. So taking this example right here on the board, look here, in this example, you're pulling the magnet away. The coil does not want to produce current. So what can a coil do to not produce current? You are pulling the magnet away from the coil. The coil can try to attract the magnet to stop it from moving. So how do you attract a north pole that is moving away? You produce a south pole. So the coil will induce current in itself such that it produces a south pole, which will cause mutual attraction between the magnet and the coil. This attraction that is caused, this will try to oppose the magnet from moving. You're pulling it away. So if the coil is trying to attract it, it's trying to stop you from pulling it away. Why is it trying to stop you from pulling it away? That is Lenz's law. It says that if you don't experience any resistance, if you can't pull it in spite of the resistance that the coil offers, you won't be able to produce or induce current. That's it. That's the entire Lenz's law in a single sentence. Just remember, you're trying to pull a magnet away, the coil will try to attract it. You're trying to push a magnet towards a coil, it'll try to repel it. No matter what you do, it will try to produce current, which produces its own magnetic field, which opposes the motion of the magnet. That is Lenz. Let me write it down as I said. Lenz's law basically states that a current carrying coil will, which is subjected to, which is subjected to a changing magnetic field or flux, doesn't matter, by moving a magnet towards or away from the coil, will induce current in itself such that the current induced produces a separate magnetic field which opposes the magnetic the first magnetic field causing it in the first place. What I'm trying to tell in fancy words is it will try to attract the magnet if it is moving away, or repel it if the first sentence was what was happening here. If you notice, if it is moving towards the coil, this is Lenz's law. In simple words, this is Lenz's law. Please make sure you understand. If you have any doubts, please feel free to ask. Okay, let's move on. I mean, those are watching it on YouTube, please type in your comments. We will try our best to reply uh, in a realistic time. Okay. The induced EMF depends on all these factors. It depends on how fast the magnet moves, how strong the magnet is, the strength of the magnetic field is, and the number of turns of the coil. Next. Again, this is what I was telling you about Lenz's law. You try to push it towards, it will try to repel it. You try to pull it away, it will try to attract. That's how current is induced. So in both the cases, current will be induced in opposite direction, because in both the cases, it's trying to do different things. Here, north and north. So it's trying to repel here. Here, south and north. So it's trying to attract here because it's moving away. So this is how Lenz's law works. Again, this is in, I would say this is basically a handshake between the Lenz's law and law of conservation of energy, because that's what it is. If you don't face any opposition, you're not doing any work. If you're not doing any work, you're not getting work done. That is, you're not inducing current. That's it. Next is Fleming's right-hand rule. Same logic, same fingers, same denotation, except here, force is producing current. Left-hand rule, current produces force. Right-hand rule, force produces current. The important application is the working of a generator, which I shall explain. For a generator, I'll name it the same so as to not confuse you. I'll name this as P, Q, R, S. The rotation seems to be clockwise. I'll explain you how the directions are. Again, I'll take two different paths here. This time it's no longer split rings. The commutator consists of slip rings. I'll name slip rings S1, carbon brush B1, slip ring S2, carbon brush B2. Again, here slip rings, you'll notice that the contacts don't change because this contact is, this will rotate like this. This contact will rotate like this, or however, in any direction. So the contact will not change. That means part P will always be connected, I guess, to S2, looks like it. And part S of the coil will always be connected to S1. Let's see how that works. Let's take the initial conditions, P, Q, R, S. Again, P and S, Q and R, their forces will be opposite directions. We'll forget them. Now, let's say coil rotates like this. That means here force acting is upwards, here force acting is downwards. So let me name them for part PQ, for part RS. So force acting on PQ is upwards. The magnetic field B is north pole to south pole, which to me, from my perspective or point of view, is to the right. So force upwards, magnetic field to the right, current induced, have to find out. Use Fleming's right-hand rule. Force upwards, magnetic field to the right. Look at my middle finger. My middle finger is pointing into the page. So on PQ, current will be induced into the page. You can see here. QRS, force acting is downwards. Magnetic field is still to the right, which means current. Here current induced was into the page. Here current induced will be out of the page, which is exactly like this. How do I know? Force downwards, magnetic field to the right. And you can see, you can't see my middle finger, but notice it's into the out of the page, like this, out of the page. So that's how you figure out the direction of current induced. So this is how current is induced. So this is direction of current induced here. As soon as it completes half rotation, please remember, P will come here. This is P, this is Q, this is R, this is S. What will happen is the rotation will be happening in the same direction, which means on PQ force will be downwards. Here it will be upwards. So for PQ, force acting is now downwards. Magnetic field B is still to the right, which means current induced I will be out of the page, which was originally the direction for RS, if you notice. For RS, force acting will be upwards. Magnetic field is still to the right, producing the current into the page. So if you notice, on PQ, current will be out of the page like this, RS inwards. So that means direction of current induced will be ulta. So in other words, current direction reverses every half a cycle. But in this part, split P was connected to, let's say, S1 or S2, doesn't matter. Take any one. It was connected to S2 only. Diagrammatically, it appears to be S2. So let me take S2. It was connected to S2, which was connected to B2. This was connected to S1, which was then connected to B1. The same will continue. The same connection will appear here as well. That means here as well, if I erase this part, S2 will still be connected to B2 and S1 will still be connected to B1. So this, the I would say the connection interchange that occurs in a motor does not occur here. S1, S2, S1, S2, same thing. This means every half a cycle, the current produced, so current produced here reverses every half a cycle. Or in other words, the current generated here is alternating current, not direct current, because the current direction keeps reversing every half a cycle, assuming the rotation is happening in the same direction, like this. This is how an AC generator works. Very similar. There are other videos from other channels which explain it equally well, in fact, even better. Khan Academy is one such channel which explains the working of the motor and generator very well, with an animation, of course. Please feel free to watch that video as well in addition to this to understand the concept much, much better. Hope that helps. Again, the induced EMF can be or is dependent on these factors: the number of turns, the area of the coil, the strength of the magnet, and the speed at which the coil is rotated. Remember, when coil goes from perpendicular to parallel, EMF will increase. Parallel back to perpendicular, decrease. Again, parallel to perpendicular, increase, but in the opposite direction, hence negative. Then perpendicular back to parallel, decrease, but in the opposite direction. This is how it occurs. So when it is perpendicular, remember, maximum number of field lines cut to the coil. Maximum number of field lines. When it is parallel, zero field lines cut. Again, when it is perpendicular, maximum field lines cut. When it is parallel, zero field lines cut. Again, when it is perpendicular, maximum field lines. So this interchanging rate of change of magnetic flux is what produces EMF or current in the coil. Please remember that. Few other things you have to understand. One is the working of a transformer. Let me explain the working of a transformer. A transformer works on the principle of electromagnetic induction. Also, quick rule, transformer works only on AC. It doesn't work on DC. I'll explain why. Let's say I give an input AC voltage. AC starts flowing through the primary coil. The AC is alternating current, which means the coil produces a varying magnetic field. Varying magnetic field. This varying magnetic field is transferred or given from the primary coil to the secondary coil through the soft iron core, which gets magnetized and demagnetized. So now secondary coil is subjected to this varying magnetic field, which means through the process of electromagnetic induction, it will now induce current in itself, producing an output voltage or a secondary voltage. So this is how an input primary voltage produces a varying magnetic field, which is then transferred from primary to secondary through a core, which is then undergoing the phenomenon of EMF, producing a secondary voltage. Now, the important question, why does transformer only work on AC, not DC? Because if you allow DC to flow in, the primary coil will produce a magnetic field, but it will not be varying. It will be uniform, which means it is incapable of producing an EMF or undergoing the phenomenon of electromagnetic induction, EMI, in the secondary coil, thereby not producing a secondary voltage at all. Current, actually, secondary voltage will be produced in the small fraction of time that it takes for current, DC current, to go from 0 to maximum. But when it reaches maximum, current produced as secondary will again go back to being 0, because current or voltage at primaries or current at primary is no longer varying. Hence, there is no current or voltage produced at the output. That's why transformer works only on AC. So transformer turns ratio, how is the formula derived? Very simple. Voltage at primary is proportional to number of turns primary. Voltage at secondary is proportional to number of turns secondary. Divide the two equations. You get Vp by Vs equals Ip by Is. This is called the turns ratio. If you increase the number of turns in secondary coil, you increase the secondary voltage over primary voltage, called as a step-up transformer. You decrease the number of turns in the secondary compared to primary, you step down the voltage, making it a step-down transformer. Remember, regardless of what happens, the power at the input or power at the primary will be equal to power at the secondary, which means power at the primary, which is voltage primary into current primary, using the formula power equals voltage into current, will be equal to power at the output, which is voltage secondary into current secondary. So equating these two, you get Vp by Vs equals Is by Ip. I think I've made a mistake here. I should have written N for number of turns. Voltage is proportional to number of turns, number of turns primary, number of turns secondary. That's it. I'm sorry for the mistake. Please make sure you get this correct. This is equal to Is by Ip because of this equation. Vp-Ip equals Vs-Is. This is your transformer turns ratio equation. Ideally, input power equals output power, but practically no transformer is perfect. So output power will always be lesser than input power. You can calculate that using efficiency, and I can make your numericals slightly more difficult using that concept. Next, the last concept to remember is power transferred. So remember, do you notice how power produced at the power station is low voltage, but it is transferred at very high voltage, which means the transformer here uses a step up. It is transferred at high voltage so that the power loss that occurs is kept at a minimum. Power loss is calculated as I square into R. You'll notice that as you increase the voltage, current will reduce. So when you reduce the current, you basically reduce your I square R losses. Some students always ask me this. Like, sir, if I just use the formula V square by R, I can just say power loss is greater because voltage is increasing, so power loss should increase. But remember, there is a reason why I'm using power loss as I square R and not V square by R. The simple reason being the loss, when current flows over long distances, the current flowing in this wire heats up the wires. And current heating up is what is causing the thermal loss or the energy loss. That is why power loss has to be I square R, not V square by R. Another reason is, if you use V square by R, you'll notice that voltage is again stepped up, which means power loss should increase, but that can't happen because increasing voltage would also increase resistance. But then those two will again interact with each other, causing a cascading effect. So power loss is I square R, not V square by R, for logical mathematical reasons. Again, that's it. This is the whole power generation, power consumption. Any doubts in this? Please let me know. Like I said, please let us know. We've discovered what diodes are. Please let us know. We will be more than happy to discuss your doubts and help you along your journey that is doing well in your IGCSE exams. Thanks, guys.